For this lesson, we are going to once again take a look at optimization problems. In this case, we're going to be focusing on optimization as it occurs in finance and economics. A few things to remind you of related to those types of problems. The most typical thing you're going to run into is going to be the notion of profit. So the idea of optimizing profit, the maximizing your profit. In that case, profit is generally regarded as revenue minus cost. This is a simplistic look at the idea of profit, but it's suitable for our purposes, and it's a good first approximation to a profit function. Revenue, although revenue is sometimes just defined as how much money is coming in as an equation, sometimes revenue is actually broken up into two different functions themselves. One of them is the price function, so how much you are selling each unit for, and then there is a generally, this isn't the function, or it's a very simple function, which is the number of units sold. And we can also complicate matters further by having a cost function. Sometimes the cost function will be based on just a formula, an algebraic model. Other times a cost function will actually, the cost of the units you create is also based on, the number of units that you sell. So this can get more complicated depending on what you're dealing with. Now I've got quite a few examples to cover in this lesson. So the approach that I'm going to take is I'm going to take my time and I'm going to set them up and I'm going to get us to the solution. But I am going to skip over steps where I feel that's something you should be able to do on your own. And of course, should you have access to me, which would be students in my class or in the school, feel free to come and talk to me about these individually. So let's go ahead and get started. You'll see what I mean once I work through this first question. Now this first question is interesting because technically this question can be done without calculus. This question can actually be done just as a quadratic where you're looking for the vertex. Now the point of what we're doing here is not to rely on that old knowledge. That old knowledge is still good and it's still valuable, but we're just going to hold that knowledge in reserve as a bit of a check here in case we run into problems with this. But the point is to use calculus for this one. So we've got a professional basketball team playing in an arena that holds 20,000 spectators. The average attendance at each game has been 14,000 spectators, and the average ticket price is $75. They've done some market research to show that for each $5 reduction in their ticket price, so if the ticket price goes down by $5, 800 more people will attend. We want to find the price. So in other words, we want to find the new ticket price that will maximize revenue. So first of all, let's just talk about revenue very quickly. In this case, revenue is the number of people attending, which would be 14,000, multiplied by the price that each one of those people paid, which was $75. But we don't want to just hold revenue at this static model. We actually want to change this. We want to allow our revenue to change, and the way that we're going to do that is, for example, we can subtract $5 off the price, and if we were to do that, it would add 800 attendance to the game. And similarly, I can actually subtract $5 multiplied by X off of the price, and that's going to add 800 times X spectators. So what I've essentially done here is I have let X represent, and you have to be fairly specific with this, so let X represent the number of, and what does it represent in this case? It is the number of $5 reductions in price. And that's important because when we solve this, if we end up with a negative answer for X, that means we actually have to increase the price. Whereas if we end up with a positive answer for X, that means we have to decrease the price. So this idea of reductions, that is tied to how we set up our equation in the first place. So that's the first thing I want to point out to you. So what we've got now, because of the way we've done this, we have revenue as a function of X. And since it's entirely a function of X, I can now take the first derivative, so r prime of X. Now it's up to you. You could go ahead and expand this and take the derivative, or you could take the derivative in line the way I'm going to using the product rule. In cases like this, it's really 6 of one, half dozen of another, which means you can choose either and you should be fine. I'm not going to multiply this out because I actually want to avoid multiplying out some of these larger numbers. I'm going to stick with things and hope to do some factoring as I go forward. So the first thing I'll do is take the derivative of this first part, which is just going to be 800, times the second part, which is 75 minus 5x, plus the first part, 14,000 plus 800x, times the derivative of the second part, which is equal to negative 5. And before I do anything more with this, I'm going to just set r prime of x equal to 0, and that's because I am trying to find my extrema. At this step, I'm trying to find any local extrema, and then I'll test to see whether or not any of them are actually absolute extrema. So now that I've set that equal to 0, and I'm just going to go, I'll write it out again. It's a bit of a formality, but sometimes we have to follow such things in math. The one thing I'll do, since I've got this, I'm going to bring that negative 5 in front, change this positive to a negative. And then I'm going to do some factoring, but because I've got 0 on this side, it's not so much that I'm going to do some factoring as I'm going to do, excuse me, I'm going to do some dividing. So the first thing I'm going to do is I take a look and notice all of these zeros. There are 0, 0, zeros. In every term where there's multiplication, we could actually divide by 100. And the way I'm going to show that is I'm going to cross out 2 zeros, which is essentially as if I divided this by 100 and divided this by 100. So I'm dividing by 100 across the board, and that's what I end up with. I get rid of all those zeros. So I've made all the numbers quite a bit smaller. The other thing I'm going to notice is I can do a division by 5. And if I divide by 5, this becomes a 1, this becomes a 1, and this becomes a 15. So once again, that has made my life easier. I could do one more, but I'm going to write things out now because I don't want things to get overly cluttered and messy. So let's go ahead and do an expansion here. So I've got 8 times 15, and that's going to give me 120. And then 8 times 1 is just going to give me minus 8x. And then over here I have negative 1 times 140, which is just going to give me minus 140. And I have negative 1 times positive 8x, which is minus 8x. And so from here I get, let's see, negative 16x. And that's going to be 120 minus 140 is minus 20. And from here, it's actually quite a bit clearer that I can see the number 4 goes into everything here. So once again, I could have done that before. Like I said, it was just starting to get a little messy. So I get 0 equals, and that's going to be negative 4x minus 5. And I bring that over, I get 5 equals negative 4x, or x equals negative 5 over 4, which is the same as x equals negative 1.25. And that's perfectly fine to write it that way. That's an exact value. That's a non-terminating, or sorry, that's a terminating decimal. Now that I've done that, we have a local extrema, but we don't know whether this is a maximum or a minimum. So the other thing we need to do is we need to consider our boundary conditions. Or our endpoints. So what are the boundaries on this? And sometimes, and this is really one of the things I wanted to focus on in this lesson, which is, so how do we come up with those boundaries? So let's take a look at the information we had here. What about this arena? What do we know about the arena? We know that the number of people that are going to be in the arena, well, we need to have someone in the arena, otherwise we don't have a game, or at least we don't have any money coming in. So we know that 14,000 plus 800x has to be greater than or equal to 0. And so from there, I end up with 800x has to be greater than or equal to negative 14,000. And like I did before, I'm going to divide by 100 immediately, just to make that a little bit easier to deal with. And so I end up with 8x is greater than or equal to negative 140. X is greater than or equal to, and that works out to be negative 17.5. And we could leave that as its exact value as well, which works out to be negative 35 over 2. So either of those is fine. So that's one of our boundaries. Now, as far as the number of people in the arena, we also know that 14,000 plus 800x, it tells us in the question the arena only seats 20,000. So that must be less than or equal to 20,000. That's our maximum crowd size. 800x is less than or equal to, so that works out to be 6,000. And when I divide that through, first of all, I divide by 100, and I end up with x is less than or equal to, and this one works out to be 7.5. So that's what I got from the arena. Now, what about our price, the amount we charge for people to get in? Well, there's no upper limit on that. There's only a lower limit, which is 0. So 75 minus 5x has to be greater than or equal to 0. 75 has to be greater than or equal to 5x. I moved the 5x over because I'm just trying to avoid dividing by a negative. It works so long as you remember that if you divide by a negative, you have to reverse the sign of the inequality. But now I can divide by 5. I end up with 15 greater than or equal to x, which is the same as x less than or equal to 15. Now, when we take a look at the boundaries we have here on a number line, I've got negative 17.5. I have to be greater than that, so greater than or equal to that. And then I've got 7.5 and I've got 15. Well, based on that, obviously this one doesn't matter. These two are the ones that matter. And so I end up with my domain is x member of negative 17.5 up to 7.5. And so when I test for maximum or minimum, I'm going to test r of negative 17.5. I'm going to test r of 7.5. And I'm going to test r of the value that we actually got, which is negative 1.25. And when you do that test, you will find that this one indeed is the maximum. But don't forget, the question actually wants to know what is the price, what is the ticket price. So my ticket price has to be 75 minus 5 times, and I warned you before that this could end up being a negative. And so if that's the case, I end up with a ticket price of, what does that work out to be? I'm just kind of curious. 5 times 1.25 plus 75, 81.25 is the recommended ticket price. Now, as you can see there, even with skipping a couple of steps, that still took quite a bit of time. So, on to exercise number 2. Exercise number 2, we're constructing a closed rectangular box with a square base. But the thing is, the interesting thing about this, or the complication here, is we're using 2 different types of wood. So I will go ahead and draw my approximation of a box. And it's got a square base, so I'm going to set those 2 dimensions to be x, and then I'll give it a height of y. We are told that this box overall has to have a volume of 4,000 cubic meters. That's a big box. And so that piece of information allows me to say that x squared y, which is base times width times height essentially, is always equal to 4,000. So that's the first piece of information that I'm going to pull out from there. The second piece of information that I'm going to get from here has to do with the cost to build this box. Now, we're told that the wood for the top and bottom costs $20 per square meter. So the cost to build this box is going to be the cost for the top and bottom plus the cost of the 4 sides. But what is the cost of the top and bottom? That's equal to $20 per square meter multiplied by the area of the top and bottom. And the cost of the 4 sides is going to be $30 multiplied by the area of 4 sides. Well, what can we say about those things? As you can see, I'm kind of chipping away at this problem. Well, the area of the top and bottom, each of the top and bottom has an area of x squared, but there are 2 of them, so that's 2x squared. Plus 30, and the area of the 4 sides, each side has an area of x times y, but there are 4 of those sides, so that becomes 4xy. And a little bit of simplification, if I wanted to, that would become 40x squared, and that would become plus 120xy. Now at this point I couldn't move forward because what I really want, and it's not just a want, I actually need cost as a function of x. In order to do that, I really need to get rid of this variable y. I could also try to get cost as a function of y. When we're taking the derivative, we don't actually care whether it's with respect to x or y. It's just we've got it ingrained so heavily that x is the independent variable and y is the dependent variable. A lot of people have a hard time shifting gears on that mentally. So I recommend you stick with what's most comfortable and familiar to you. Now the way that we're going to get rid of this y is we're going to come back up here and make use of this relationship, and we're going to rewrite it as y equals 4,000 over x squared. And by doing that, it allows me to now write this as c of x is equal to 40, that's a really awful 40x squared plus 120x, but we're going to replace that y with 4,000 over x squared. And notice that in doing that, this x divides out and becomes 1, and this x squared divides out, just becoming x to the power 1. So my c of x is equal to 40x squared, and I'm going to leave that 120 times 4,000 all divided by x. If you prefer, you could write this, you could bring this up and write this as x to the negative 1 for this next step where we take the derivative. So taking the derivative, c prime of x, I'm going to give myself a little bit more space over here at the side. So just using the power rule there, we end up with 80 multiplied by x, and then keeping in mind that this power of x in the denominator could also be written with a negative exponent, this works out to be negative 120 times 4,000 over x squared. We could have also written that using the negative exponent, and that would have worked just fine. So we could have also written that as 80x minus 120 times 4,000 times x to the negative 2. That would have worked just as well. So regardless of which path you take, they're equivalent expressions. They mean the same thing. So now that we've got that, we are looking for local extrema. So we are going to set c prime of x equal to 0. And so we get 0 equals 80x minus 120 times 4,000 over x squared. At this point, there's actually very little need for me to expand out this 120 times 4,000. It actually turns out to be more useful for me to leave it, I think, the way it is. But there is some simplification I can do here. What I'm going to do is I'm going to actually divide everything by 40. When I divide 0 by 40, that just gives me 0. When I divide 80 by 40, that actually gives me 2, so that becomes 2x. And when I divide 120 by 40, that gives me 3. So now I get 3 times 4,000, which I thought of going ahead and writing as 12,000 there, but I'm not going to. And then the next thing I'm going to do, I realize I could have done this in one step, I'm going to divide everything by 2. And when I divide everything by 2, well, 0 divided by 2, well, that's still 0, so I don't really need to do that. 2 divided by 2 just gives me 1, and 4,000 divided by 2 gives me 2000. So now I end up with a final simplified equation of x minus, now I'm going to go ahead and simplify this, 3 times 2000 is 6000 over x squared. I'm going to bring this term to the left side. I end up with 6000 over x squared is equal to x. I'm going to cross multiply by my x value, so I end up with 6000 is equal to x cubed. Now this is something, we've had this x in the denominator the whole time, so we've always known that x was not allowed to be equal to 0. But now that I've cross multiplied it through, it's probably a good idea for me to make note of the fact that x cannot be 0, because essentially at this point I've lost that information. So I make a mental note of it. I make a deliberate, it's not a mental note, I make a deliberate note as I'm doing my work to say that I know that x cannot be equal to 0, and x in fact turns out to be equal to the cube root of 6000. And if we wanted that in a slightly more useful form, taking the cube root of 6000, we end up with x is approximately equal to 18.1712. Now I don't know yet which of these forms I'm going to need, if I need one or both, or, well, hopefully I could use at least one of them. So now that I've found that, let's go back, take a look at what the question's asking for one more time here. We want to find the dimensions that minimize the cost of building the box. So we have found a local minimum that satisfy these conditions, but we have found a local extreme value, a local extrema. We don't know if it's a maximum or a minimum, and that's why I'm constantly reminding you that you do have to consider what are known as your endpoints, and I sometimes refer to those as your boundary conditions, which is just another kind of more general fancy way of talking about endpoints. So in this case, what are the endpoints? Now you might think, if we talk about this in terms of the dimensions of a box, you might think, oh, well, the endpoints in this case, that would be when x is equal to 0. But if you take another moment to think about that, if x goes to 0, and you can actually see that right here, so I want you to pay particular attention to this equation. If x goes to 0, then what does that say y has to be? Because we have this restriction imposed upon us that 4,000 has to be the volume of the box. So this isn't just a matter of saying, sometimes students and teachers will have discussions about saying, well, x can't be 0 because if x were 0, then it would have 0 length or 0 width, and it'd have an area of 0 or a volume of 0. That's not really a box, or that's not really a square. And that's it's a valid argument from a realistic point of view, but that actually doesn't stop x from going to 0. But in this case, we're actually told that this box has a volume of 4,000 cubic meters. That now does place a restriction here, because there's no way for x to go to 0, because if it did go to 0, that would require y to be infinitely large. The same thing is true the other way around, which is that y can also not go to 0, because if the height of this box were 0, then the base of it would have to be infinitely large. And so what we end up with is, in this case, our domain ends up being x is a member of 0 to infinity, but it can't be 0, and we actually discovered that here as well. And it also can't be infinity, because that doesn't make any sense to us. So as it turns out, we cannot test our endpoints. And so if we can't test our endpoints, then it raises the question, is this a local max or min? And actually, not only does it raise the question of this is a local max or min, but since this is the only extrema that we can detect, since we can't detect endpoints, that means we cannot have absolute extrema here. So these cannot be our absolute. extrema, which means this local max or min has to be also the absolute max or min. So that being the case, how do we decide that? There are two ways that we could decide that. So our first option here is we could try the limit as x approaches 0. We could approach 0 of c of x, and we could also try the limit as x approaches infinity of c of x. Now, we haven't really talked about this one. I'm sure that many of you could piece that one together. We've maybe talked about it in the context of horizontal and oblique asymptotes. We've talked about it, but we haven't really talked about it directly. However, what I'm going to suggest is an alternative, which is, why don't we try values near x, which equals the cube root of 6,000. So what we can do instead, rather than doing this, we can just try values near x equals the cube root of 6,000 and just find out whether or not this represents a local maximum or a local minimum. Because we can't test the endpoints, that would also provide us with an absolute maximum or an absolute minimum. Now, we are, of course, looking for the dimensions that minimize the cost of building the box. So it stands to reason that everything except for a particular value is going to make this box more expensive. So it turns out that this is the absolute minimum. This is our answer. And so what we could do instead is we could try x is equal to the cube root of 6,000 plus 1. We could try that. But I think I might prefer, since I went ahead and figured out by calculation what this was equal to, well, why don't we just try 18? And x equals, and let's try another value, 19. 18 and 19 are on this domain, 0 to infinity, and we can go ahead and sub those in. And if we sub them in, what we end up finding out is that x equal the cube root of 6,000, which is the same as x approximately equal to 18 point, and what was it? I'll just move up a little bit, 1712, is the absolute minimum. So we go ahead and try those, and we find out that's our absolute minimum. And let's just double check, because what does the question actually want? The question wants us to find the dimensions that minimize the cost. So the dimensions are, well, x we have found, that's 18.1712, and then the y value comes from this, 4,000 over x squared. So I come back down here, and so therefore the dimensions are, and I'm going to round that, I'm going to say that's 18.2 centimeters. Centimeters or meters? Meters. This is a big box. 18.2 meters by 18.2 meters. And then I do my last calculation, which was 4,000 divided by that answer squared, which is by, and that works out to be 12.1 meters. So that is those are the dimensions of the box that will give us the lowest cost possible for the materials that we've chosen. So we have a local furniture manufacturer who is selling cedar patio sets. The company can sell X units each month at a price of 1,000 minus X. So that's the first thing we have to look at. Notice this is lowercase p. And so sometimes, as I warned you, revenue is sometimes expressed in terms of the number of units sold multiplied by the price per unit, which is lowercase p. So in this case, we have X units sold and we have 1,000 minus X, which is the number of units sold for that number. Sorry, that's the price per unit for that many units sold. Then we also need to consider the cost. Well, the cost function is given to us. So profit, which is capital P, is equal to the revenue, which is X times 1,000 minus X, minus the cost, which is going to be 3,000 plus 19x squared. And in this case, I'm going to go ahead. In the last one, I took the derivative in line. This one's just a little bit, it's actually not really that bad, but I'm going to go ahead and approach it a different way. So I'm going to go ahead and expand this out. And so I end up with, and this is profit, and this is actually profit as a function of X. And so I end up with my profit function being negative 20 x squared, and that's going to be, let's see, plus 1000x minus 3000. This is actually a quadratic, so once again, this is a parabola. This is a parabola that opens down because of this leading coefficient. So we know whatever we find here, the local extrema is going to be a maximum. And you can use that as an argument if you can't figure out how to do the boundary conditions. But again, for problems in this calculus course, you're expected to be looking at boundary conditions. So let's take the derivative of that, and we end up with negative 40x plus 1000. And now we're going to solve, so we're going to set p prime of x equal to 0. So I get 0 equals negative 40x plus 1000, and that works out to be x is equal to 25. And once again, so we've got our solution. We know that this is the maximum, but we really do need to check our boundaries. And so what are the boundaries for a question like this? We have to sell something in order for us to have a product. So we know that x must be greater than or equal to 0. Now x can be 0. That doesn't cause any mathematical problems. It just means we have a really lousy product. Nobody wants to buy it. The price at which I sell my product also has to be greater than or equal to 0. So 1000 minus x must be greater than or equal to 0, which means that 1000 must be greater than or equal to x, which is another way of saying x has to be less than or equal to 1000. So we can only sell, we have to sell something, and we can only sell up to 1000. If we sell 1000 of these units, the price drops down to 0, and we're not going to make any money. What about the cost function? Are there any restrictions on the cost function? Well, the cost can be as high as can be if we're dumb enough to pay it. But there is a minimum on the cost. The cost has to be greater than or equal to 0. So we get 3000 plus 19x squared has to be greater than or equal to 0. But if you take a moment to think about this, this is always true. So that's not a condition, because 3000 is a positive number. 19x squared is always going to be a positive number because the x squared is positive. So this is always true. So in this case, what is our closed interval? It's going to be between 0 and 1000. Oop, not a round bracket. That should be a square bracket. And so we would test x equals 0, x equal 1000, and x equal to 25. And this one is going to be the maximum. And I know that already because of the very simple quadratic equation that I got for my profit. That was probably a lot longer than I wanted it to be. I went through it at the best pace I could without sacrificing the information that I wanted to convey. I think my writing got pretty sloppy at times there. So that's it. Some practice to work on here from your textbook. As you can see, this is very much like all the other problems we've done. It's just setting up a different kind of flavor of these problems. And I really emphasize the idea of boundary conditions in this lesson, which I think is an important thing. If you haven't got that really ingrained as a habit yet, I want you to redouble your efforts and make sure that you're focusing on that as you're finishing up these problems, you're thinking about those boundaries.